and then share screen, the usual routine. Let's get this going here. Mine. All right, let's see here. Okay. Okay, that looks good. I wonder if there's a way that I can share screen that would make it larger. I mean, like expand it out to the right and left. I wonder if there's a way of doing that. Is there a way to rotate it? Maybe I'll experiment with that and see if that can be done. Make better use of the real estate here. Maybe somebody knows they can tell me. All right, so let's see. This is the wrong page. I want to do this page. All right, so to start with what we did last time, an overview of it, we considered a series of coordinate transformations on the state space, or you might call it the phase space, of the classical electromagnetic field, starting with the case of the free field in which there's no matter. The state space or phase space is the space in which a single point gives you all the information you need to predict the future evolution of the field. So, for example, one description of that is to say that the state space contains the vector potential A in its first time derivative. Because they satisfy second order differential equations, this is a complete set of initial conditions. It's understood here that the vector potential is transverse. We found that an equivalent description was in terms of the mode vectors, what I call C sub k's. These are given in terms of the A's and dAdt's by a Fourier series given down here. The C sub k's are basically the mode, the amplitudes, complex amplitudes of the various plane waves that constitute the solutions. And this equations here give you the A's and A dots in terms of the C's, and you can solve for them other way around, and you can get the C's in terms of the A's and A dots by these equations down below. But anyway, that's the first coordinate transformation there. That simplifies the equations of motion. The second transformation takes the amplitude vectors ck and turns them into what I just call the mode amplitude c sub lambda. The idea is this: you take the c sub k's and you write them, since they're transverse, you write them as a linear combination of the transverse polarization vectors epsilon sub k mu. The mu here is a polarization index. It runs from 1 to 2, and the k runs over all the lattice points in k space. The combination of k and mu is what we call a mode. It specifies both the direction of propagation as well as the polarization. And I use the abbreviation lambda for that. It saves a lot of writing to do that. So epsilon k mu are the polarization vectors, can also be written as epsilon sub lambda. Anyway, expanding the amplitude vectors in terms of the polarization vectors gives me what I call the mode amplitudes, which are the ck mu's, which are otherwise we'll call c sub lambdas. And that's the next set of variables. This is a fairly simple coordinate transformation to go from between these two, but the c lambda is the new set of coordinates. Then, having gotten those, we looked at the time evolution of the c lambdas for the free field, saw that it looked like harmonic oscillator evolution, allowing us to guess that the q's and the p's, which I call q lambda and p lambda, of the system are proportional to the real and imaginary parts of the c lambda. And then, so we ultimately were able to determine what that proportionality constant is. It's this square root thing here. And the way we did that was we said, well, the Hamiltonian needs to be the sum of harmonic oscillators to make the evolution of the c lambdas come out right. But if we insist that the Hamiltonian is also the energy in the field, then by taking the Fourier series for E and B and plugging in and doing the integral, we not only verify that the answer is indeed a sum of harmonic oscillators, we also get the coefficients that we need here to connect the C's with the Q's and the P's. And that takes us to the Next, that takes us to this stage of transformations. These Q's and P's are now canonical variables. And moreover, we now have the Hamiltonian as well. So at this stage, what we've got is a Hamiltonian for the free field, as well as the canonical Q's and P's and the series of coordinate transformations that takes you back to the fields that we started with. So that's part of what we did in the last lecture. Now, here's something else that we did, is having done that for the free field, we worked on the interacting field. And to do that, we kept the coordinate transformations exactly the same as for the free field. Now, this is a common strategy in dealing with differential equations, in case you've ever dealt with the Lagrange's method of variation of parameters, which should be taught in courses in ODEs, although I don't know what they teach nowadays. But in any case, that's one of the basic ideas of that method. You use a coordinate transformation motivated by the free field in order to put the equations of motion for the interacting field in a useful form. So having done that, the definitions of the various coordinates that we went through don't change, but what does change are the equations of motion. For example, we find the vector potential is driven by a wave operator, but on the right-hand side, there are now the transverse components of the current. In terms of the amplitudes or the mode amplitudes, we get equations that look like this. The left-hand sides of these two equations here would be 0 for the free field, but for the interacting field, it's driven by some component of the transverse current. Here it's the kth Fourier component of the transverse current, and here it's what I call J sub k, J sub transverse lambda, where that just involves dotting the transverse component of J with a polarization vector epsilon lambda to pick out that component. In any case, these are now essentially driven harmonic oscillator equations. That's what they are. All right. Now, in the case of the free field, we ended up determining that Hamilton's equations applied to that harmonic oscillator Hamiltonian, the H that we had there, are actually equivalent, tracing back through the coordinate transformations, to Maxwell's equations for the free field. So we have a Hamiltonian description of the free field. For the interacting field, we can do the same thing, but we're going to need a new Hamiltonian. The old Hamiltonian, it needs to be generalized to include the interactions with the matter. And so that's the first task that we have before us tonight, is to do that. So here's what we're going to do. We're going to guess, as we did before, that the Hamiltonian for the interacting field is just the total energy. But the total energy for the interacting field, of course, includes a matter term as well. So let's write down the energy for the interacting electromagnetic field with matter. And that expression is the following. It's the sum over the particles, which I'm indexing by alpha. Their mass is m sub alpha times the velocity is v alpha squared, and I have to divide by 2. That, of course, is just the kinetic energy of the particles, and it's a non-relativistic kinetic energy. And then we add to this the field energy, which is 1 over 8 pi, the integral over all space d cubed x of e squared plus b squared. Actually, since we're using box normalization, it's really not the integral over all space, it's just the integral over a box, but later on we'll let the volume of the box go to infinity, and then it'll turn into that. All right. In any case, this is the expression for the energy of the particles plus the field. Now, one question you might have at this point is how do I know that that's the expression for the energy, and how do I know that it's right? For example, the kinetic energy of the particles is clear enough and the field energy is clear enough, but maybe you might be wondering, where's the potential energy of the particles? That seems to be necessary to get the particle motion right. Well, I'll answer those questions in a minute, but let me give you at least 2 or 3 reasons why we know that this is the energy of the system. The first, and I'll just outline them. The first reason is Noether's theorem. Noether's theorem says or associates symmetries with conserved quantities, and it's based on Lagrangians. If we take the Lagrangian for the matter, non-relativistic Lagrangian, and add to it the Lagrangian for the electromagnetic field to get the total Lagrangian for the matter field system, this is invariant under time translations, and in general that leads to a conserved quantity which we identify with the energy. And if you work that out using the machinery of Noether's theorem, you find that this is what comes out. This is the conserved quantity. Also, that energy, that quantity under time translations invariance is more or less by definition, that is the energy of the system. So that's why I call it H. I'll call it H here for the energy. A second point of view is to take the stress energy tensor of both the matter and the field and add them together to get the total stress energy tensor of the system. The 0, component of that is the energy density. And if you integrate that over all space to get the total energy, then again, this is the expression that you get. I'm assuming that you're familiar with stress energy tensors. They're taught in undergraduate courses, and I'm hoping you did them in 209 too. If not, I'm going to complain to Martin for not doing it. In any case, that's the second approach to this. The stress energy tensor also gives you conservation of momentum too, or the total momentum of the field, and I'll come back to that later on. Yet a third approach to understanding why this is the correct expression for the energy is simply to compute the time derivative of it, dH dt, and that should be equal to 0. And how do I know what that is? Well, I just use the chain rule in the various variables here. So using the chain rule in the first term, I get the sum on alpha of m alpha times v alpha dotted into v alpha dot. That's taking the derivative of v alpha squared. And then for the field energy, I get 1 over 4 pi. There's a factor of 2 on doing the chain rule. I get d cubed x integral over all space. And then what I get is the electric field dotted into the time derivative of the electric field, plus the magnetic field dotted into the time derivative of the magnetic field. Well, in the first term, the mass times the acceleration v alpha dot is just given by the Newton-Lorentz equations of motion. It's the charge q alpha times the electric field evaluated at the particle position r alpha plus a v alpha over c velocity crossed into the magnetic field evaluated at the same position, like that.
Professor?
Yes,
Is there any way you could turn up the light? Your screen's just a little dark.
Yeah, the screen is dark, and let me see if I can tilt this a little bit to make more light. That didn't work. Let me see what I can do here.
Try unfocusing it and then focusing it again.
Yeah. Good. Is that better?
Thank you.
Yeah, thank you very much for letting me know those things. If you have any objection to the way things are going, please let me know, because then I can stop and fix it. I really appreciate you doing that. By the way, somebody said that my writing was too small, and so and it was too. So one of the things I've done is switch to a pen that has a larger point. And I think this has increased the size of the writing by about 25 or 30%. If that's not enough, I can go to even bigger pen points. But anyway, let me know if that's a problem. I don't want to go too big because I don't have enough room if I do that. But anyway, this should be an improvement over what it was a couple of weeks ago. All right. In any case, these are what I call the Newton-Lorentz equations of motion for a charged particle in an electromagnetic field, which you should be familiar with. As far as the E dot is concerned, that comes from Maxwell's equations. E dot is really the Ampere's law. It's C times del cross B. And if there were matter around, well, there is matter around here, there would be a current as well, which is plus 4 pi j. It's minus 4 pi j. And then likewise, the B dot is given by Faraday's law. That's minus C times del cross E. And if we take these equations of motion for the matter in the field, and we plug them in to this expression here for dEh dt, and then just run through the algebra, lo and behold, when the smoke clears, the answer is 0. You can check that for yourself. But this is just a direct verification that this is indeed a constant of motion. Doesn't prove it's the energy, but other considerations show that it is. All right, in any case, this is all a bunch of arguments for why this is the correct expression for the energy of the classical field interacting with the matter, under the assumption that we use a non-relativistic model for the matter. We could have used a relativistic model for the matter, but I don't want to do that because our initial applications will be to non-relativistic systems, and also the relativistic treatment of this problem is much more complicated than the non-relativistic one. So we'll start with the easy problems first. All right. Now then, so that's the Hamiltonian. Now let's see. We want to, what we'd like to do is to express this in terms of these variable coordinate transformations we just went through. Ultimately, we'd like to write it in terms of Q's and P's for not only for the field, but also for the matter. So to begin that process, let's work on the electric field energy, and let's pick out let's take the electric part of the field energy here. This is 1 over 8 pi integral d cubed x of E squared. But E squared is the square of the electric field. If we break the electric field into its longitudinal and transverse components, E longitudinal plus E transverse squared, we get that under the integral. Now, the cross terms in this involve the dot product of the transverse and electric components of the electric field. At a given point of space, real space, I mean x, those two components are not orthogonal to one another. But if you integrate over all space, then the result is 0 because they're orthogonal in K space. This is the Parsifal identity, which I made reference to 1 or 2 lectures ago. And the result of this is the cross terms in this expression are actually equal to 0. And this can be written as 1 over 8 pi, the integral d cubed x, of just the square of the longitudinal electric field plus the square of the transverse electric field. I'll remind you that in the case of the free field, we didn't have any longitudinal field. It was purely transverse, but now we do. So let's look at this. So let's look at the longitudinal field energy. That's going to be 1 over 8 pi integral d cubed x. And then E longitudinal squared is the same thing as gradient of phi squared because that's what E longitudinal is. I'll remind you that the two terms in the expression for the electric field in terms of the potentials, those are really the longitudinal and transverse components of the electric field if we use Coulomb gauge. So this is the longitudinal part. Now del phi squared, we can play some games and integrate by parts. This is the divergence of phi times del phi minus phi times del squared phi, just by vector identity. And of these, the integral of the first term is 0 because by Gauss's law, we can transform the divergence into a surface integral. And if we assume that phi vanishes at infinity, then the surface integral goes to 0. It also works for periodic boundary conditions, which is actually what we're using here, because then you find that the integral over one face cancels with the integral over the opposite face. They're periodic, but the unit vectors, the face vectors are pointing in opposite directions, so they cancel. So either for boundary conditions vanishing at infinity or periodic boundary conditions, that term goes to 0. So meanwhile, what we're left with is the second term, which is minus phi del squared phi. But del squared phi is equal to minus 4 pi rho, which is one of the equations, one of Maxwell's equations written in Coulomb gauge. And so combining this together, this longitudinal electric field energy turns into 1/2 the integral over a 3-dimensional space of rho times phi, simply that. Familiar expression from electrostatics, but I keep saying we're not doing electrostatics. This is fully electrodynamics. Anyway, when we work this, we can work this out further using our model for the matter, which was point charges. I introduced this in the last lecture. We can write this as integral d cubed x. And then for the charge density, we'll write it this way as the sum on the particles alpha, the charge q alpha, a Dirac delta function of x minus r sub alpha, like that. And then there's going to be another expression for phi, which I'll fill in a moment. But let me point out that the rho here, this rho means rho of x. It means the charge density at position x. That's what you're integrating over here. The x is the field point at which the charge density is evaluated, but the r alphas are the positions of the particles. So the charge density is a delta function on top of where the particle is multiplied by the charge. That's the idea here. As far as the scalar potential is concerned, we worked that out too. That's q alpha divided by the Coulomb denominator of x minus r alpha vector. This is nothing but the non-retarded Coulomb potential due to particle alpha. I'm sorry, it's in the, some stuff's in the way there, at field position x. Now then, because of these delta functions, this integral can be done. And it's pretty easy to do. And what you end up with is a sum on alpha and beta. Oh, excuse me, I did this wrong. This sum on alpha is for rho. As for phi, what I want is a sum on beta. Let me call it q sub beta here and r beta there. It's a different sums. There's two different sums. We don't want the indices to collide with each other. Anyway, taking that into account and then doing the delta function integral, this gives me the sum on alpha, double sum on alpha and beta of q alpha times q beta divided by the Coulomb denominator r alpha minus r beta, which you can recognize as being non-retarded instantaneous electrostatic Coulomb, nominally electrostatic Coulomb interaction of the charged particles among themselves. So that answers our question up above, if you had it, about where is the potential energy. Potential energy is hiding in the longitudinal component of the electric field, and working out in detail, this is what we get. Now, there is a problem with this result, however, which is that what happens when you look at the diagonal elements, alpha equals beta, because in that case, the denominator goes to 0, and the answer then gives us an infinity. We get an infinite contribution to the potential energy of the particles among themselves. Really, if alpha is equal to beta, it's the potential energy of the particle with itself. That is to say, it's the self-potential energy. You know, if you have a charged particle, and if Coulomb's law is strictly valid, so you've got the electric field going out, so the electric field is proportional to 1 over r squared. If you then compute the total electric field energy, which is the integral over all space of E squared, the E squared, of course, goes like now 1 over r to the 4th, and you find that this integral diverges, gives you an infinite answer. This is sometimes regarded as the infinite self-energy of a charged particle due to its Coulomb field, sometimes called that. You know, energy is equivalent to mass, E equals mc squared. So if the electric field around a charged particle, which nominally satisfies Coulomb's law, gave an energy density like this, and if that energy were, equivalent to mass by the Einstein relation, then it would follow that there's an infinite amount of mass in the electric field. And this, in fact, is a paradox of not only point particles, the notion of point particles and Coulomb fields in classical electrodynamics, but it's also a not just a paradox. It's actually it's a flaw. It's a logical inconsistency in classical electrodynamics of particles and fields, and it has a long history in which it's troubled people. There's an old idea that goes back to Abraham and Lorentz from around 1900 thereabouts. And the idea was that since there is energy in the potential, electrostatic potential of a charged particle, like the electron, which had only recently been discovered in those days, and since energy is equivalent to mass, something else had only recently been discovered in those days, the interesting idea arose that perhaps what we think of as the inertial mass of the electron is actually nothing but field energy mass. Maybe it totally comes from the field. Well, it's an appealing idea, but the problem with it is that energy, once we compute it, turns out to be infinite. So obviously one way to fix that up would be to say, well, maybe the electron's not really a point charge. Maybe it's got a charge distribution over some small sphere or something. That would round out the infinity. And if you do that, you can find the radius over which the smearing would have to take place. It's called the classical radius of the electron, and it's about 10 to the minus 13 centimeters. In any case, that idea also runs into difficulties, because if there were a charge distribution and not a point charge, then there would have to be some non-electromagnetic forces holding the little sphere charged together to keep it from exploding, you see, by blowing itself apart, because of the different charge elements would repel one another. So then you need to introduce a new field which has its own stress energy tensor. And the net effect is that you end up with a theory that really isn't very attractive. And so nothing actually ever came of that, but it led to but it did draw attention to the problem in classical electrodynamics of the infinite self-energy of charged particles. Now that problem, as it turns out, at least is the usual a doctrine in this business, that problem cannot be cured at the classical level. It requires quantum mechanics and the program of renormalization to cure that problem, that infinity. But in any case, it's making its appearance here in this purely classical calculation that we're doing. We're going to solve that problem here by just simply throwing away the diagonal terms. Instead of summing on all alpha and beta, we're just going to sum on alpha not equals to beta. And if you do that, then it means that the electrostatic force on a given particle comes strictly from other particles and not from the particle itself. That's normally what we assume when we have interactions between particles anyway, so that's not too shocking a statement to make. But nevertheless, this is a this is indeed a troubling aspect of what we're doing here. But if we do that, then what we've got is the standard potential energy, electrostatic potential energy of interaction added to the kinetic energy, which gives us what we might call a matter Hamiltonian. And the rest of it we can call the field Hamiltonian. So let's take that point of view and let's write that out. So if we do that, then what we get is we get we get the total Hamiltonian as a Hamiltonian from the matter plus a Hamiltonian from the field. And so the Hamiltonian from the matter then is going to be equal to 1/2 the sum on it's just the kinetic energy, 1/2 the sum of m alpha times the velocity squared, v alpha squared. But then we also add this potential energy, alpha naught equals to beta, q alpha q beta divided by the Coulomb denominator between the two particles. Notice that it's non-retarded, which means that it's not really quite right. But it's not the whole story either, because there's also the electromagnetic part, and that electromagnetic part is going to be 1 over 8 pi, the integral d cubed x of now just simply E transverse squared plus the magnetic field squared. The magnetic field is always transverse with or without the matter, but the electric field has, in the presence of matter, has both a longitudinal and a transverse part, and only the transverse part is left because the longitudinal part got put up here. Well, we'd like to take this field part of the Hamiltonian and write it in terms of our Q's and our P's. Well, the way to do that is to take the Fourier series for E transverse and B. Let me see if I can find the correct sheets of paper that I need here. As I summarized earlier, the various coordinate transformations that we did, and as I said, they were based on the free field, and we're still using those, even for the same coordinate transformations, even for the interacting field. Well, if you do this for the free field, you can write out, here's a summary of it. It's mode, you get the mode expansions of the fields. This was based on the free field, but these same mode expansions are valid in the interacting field too, because that's our choice, is we're keeping the coordinate transformations all the same. So for example, here's the vector potential in the time derivative of it, written in terms of the mode amplitude c lambda. The transverse electric field is just a constant times the time derivative dA dt. So the Fourier series for E transverse is almost the same as that for dA dt, and here it is here with the mode amplitude c lambda appearing. The magnetic field, I take the curl of A. The curl of A brings down IK cross coming from the exponential that crossed into the polarization vectors, and here's the magnetic field. So these are the Fourier series for the electric and transverse electric and magnetic fields in terms of the mode amplitudes. So we can take those and we can plug them into that integral and actually do the integral to get the electromagnetic Hamiltonian. But we don't need to do any more work to do that, because we already did that for the free field, and the answers are going to be the same because the definitions of the mode expansion is the same. And so the result is, to go back to this electromagnetic Hamiltonian, this just turns into the sum on modes lambda of omega lambda over 2 times the harmonic oscillator q lambda squared plus p lambda squared. Same as for the non-interacting field. All right. So we get to save some work that way. Now, so this is approaching the Hamiltonian that we want to work with for the interacting field. However, drawing attention to the matter Hamiltonian, we'll recall that Hamiltonians in general, it's customary to express them in terms of Q's and P's rather than in terms of, does it say, positions and momenta, rather than in terms of positions and velocities. But this Hamiltonian is expressed in terms of a velocity here. So we'd like to write it in terms of a momenta. Well, let's make the guess that the definition of the momentum we want is the same one that we've been using in this course so far for particles in magnetic fields. That is to say that it should be the mass m alpha times the velocity v alpha plus the charge q alpha over c times the vector potential A evaluated at the particle position AR alpha. And if we do that and we take this matter Hamiltonian and we express it in terms of momenta instead of velocities, then the Hamiltonian for the matter is equal to the sum over particles alpha 1 over 2 m alpha, familiar looking Hamiltonian, momentum P alpha minus Q alpha over C times the vector potential A evaluated at particle position R alpha, quantity squared, plus the potential energy, which I'll just copy here, electrostatic potential energy Q alpha Q beta divided by Coulomb denominator, R alpha minus R beta. And if we do this, we now have in the matter Hamiltonian, which I'll box off here, and in the electromagnetic field Hamiltonian, which I'll box off there, these are the two terms which when added together give us the total Hamiltonian, now expressed purely in terms of Q's and P's. By the way, if you look at this matter Hamiltonian, so the total Hamiltonian then is now going to be a function of the particle positions, R alpha, the particle momenta, P alpha, and then the Q lambdas and P lambdas, which are the Q's and the P's of the field. And with any luck, Hamilton's equations applied to this should give us equations of motion equivalent to those for the interacting field. That is to say, ultimately, Maxwell's equations with sources. Moreover, the sources should be driven by the Newton-Lorentz equations of motion. All right, now, one thing to point out here is that the formulas I've written down are slightly deceptive. If you look at what I've written down for H matter here, you see it depends on the particle position R alpha there and also in the potential energy and the momentum there, P alpha, but you don't see any field variables there. Whereas the field Hamiltonian just depends on the field Q's and P's and doesn't look like it depends on the particle Q's and P's. In fact, it doesn't. It just depends on the field Q's and P's. This is a little bit deceptive because the vector potential which appears here, this is the vector potential evaluated at the particle position R alpha. But our vector potential, if we go back to our Fourier series for the vector potential, here it is. It's given right here. It's given here into the mode amplitude C lambda. Remember, those are proportional to Q plus IP for the field. So this is the vector potential evaluated at an arbitrary field point X. So that's what the X is that appears in the exponent here. And the X is not an observable, it's just the place at which we evaluate the vector potential. However, in this Hamiltonian, the vector potential is evaluated at the particle position. That is an observable, that's where the particle is. So this A here, number one, is to be understood as this Fourier series, and because the C's depend on the Q's and the P's of the field, so does the A. And moreover, the X is replaced by the particle position, and that's what goes in the exponent as well. And so in fact, it's this A here, which more properly should be written as A as a function of the particle position as well as the Q lambdas and P lambdas of the field. This is the thing that provides the coupling between the matter and the radiation, and ultimately is responsible for the emission and absorption of radiation by the matter. All right then. So this is most of what we want. We've gotten the coordinate transformations we want, and we've gotten the Hamiltonian for the combined matter field system. There is a task that we need to perform, however, because we did a lot of guesses, several guesses in deriving this Hamiltonian. And so what we really ought to do is to carry out Hamilton's equations, that R alpha dot is equal to partial of H with respect to P alpha. And there's going to be three more for the other variables, P alpha, Q lambda, and P lambda, write them all out. And then to show, tracing them back through the series of coordinate transformations, that they ultimately imply the original Maxwell's equations driven by matter. And that's a task that I'll leave to you as an exercise. When you go through it, you find that it works, so our guesses were right. And thus we have a Hamiltonian for the classical field. Now, interacting with matter. Now then.
One quick question.
Yes.
So we know that electromagnetism is a gauge theory, and it comes with the constraint being the gauge symmetry, right? So would you have to add in an extra constraint term to the Hamiltonian, or is that already taken care of?
No, the reason is we chose Coulomb gauge, which fixes the gauge. So what that means is that all the non-physical gauge degrees of freedom are essentially frozen out by the choice of gauge.
I
And
gotcha. I didn't know you could
only the real degrees of freedom are left, and those are the Q's and the P's that we have here. those are actually 2 degrees of freedom for each K vector in K space, each point in K space. That's because of the 2 transverse polarizations. That's why the mode index is K mu here, but it's 2 there's 2 per point in K space. If you do a covariant formulation of this, then you end up with 2 extra degrees of freedoms, the longitudinal and scalar photons, but then they get eliminated by constraints when you come to getting physical answers. So you're back to really only 2 real degrees of freedom. All right. The use of Coulomb gauge in this manner is the simplest way of dealing with these issues involving gauge invariance, but those are definitely big issues if you want to do covariant quantization of the problem. All right, now, so we're almost done with the classical mechanics here. There's only one further change I want to make, which is kind of superficial, but that is to introduce alternative variables to the Q's and the P's that are more useful in practice. I'll call them A lambda and A lambda star, and we'll give them names that are called normal variables. These are classical variables, which are the analogs of the creation and annihilation operators in quantum mechanics. The A lambda is defined as Q lambda plus IP lambda divided by the square root of 2h bar. And A lambda star is just the complex conjugate of it. Comes in with a minus IP lambda divided by the square root of 2h bar, like this. And these are just the definitions of A's and A daggers, except just reinterpreted as classical transformations. And if we do this, then we can express not only the Hamiltonian, but also the vector potential and so on in terms of A's and A daggers, excuse me, A's and A stars. So for example, the Hamiltonian turns into, you can kind of see that A times A stars gives you Q squared plus P squared. So where's our matter Hamiltonian, or excuse me, our field Hamiltonian? Where is it? It's right up here. It's off the charts is what it is. It's right up here. It's this thing. So this is quite easily turns into the sum on modes lambda of h bar omega lambda times A lambda star times A lambda. It's basically the absolute value of the normal variable. But this is the Hamiltonian expressed in terms of normal variables. Now this is still classical, and you might wonder why I'm introducing h bar into classical formulas. And the answer is this makes the later steps when I want to quantize more convenient, and it doesn't hurt anything to put an h bar in there. But as I say, this is still classical. In any case, the Hamiltonian, this is the field part of the Hamiltonian, the electromagnetic part. As far as the matter part, that involves the vector potential, which in turn calls our attention to the fields. So again, let me produce some summaries here for you. This saves a lot of writing because it takes all night to write this out. Is that I have on this page here the mode expansions of the fields, and I previously expanded the vector potential, its time derivative of the transverse electric field and the magnetic field in terms of the C lambdas and C lambda stars. But the C lambdas are proportional to the normal variables, the A lambdas. And if you take into account the factors that join them, you end up with these 3 Fourier series down below for the vector potential, the transverse electric field, and the magnetic field. The prefactor has changed somewhat. And now I've got A lambdas and A lambda stars in there instead of C lambdas, okay? These are the normal variables appearing in here. There and there's the A lambdas and A lambda stars. And the rest of this is just straightforward transformations from these Fourier series. Now these are close to the final version of the Fourier series that we want for the fields, expressing them in terms of normal variables. All right. And that pretty much ends what I want to say about the classical field. And so allow me to ask if there's any questions then before I go on to the quantum field, the quantum mechanics. Well, so we have a classical description now. We have the Hamiltonian and we have canonical variables, the R alpha, P alpha, the Q lambda, and P lambda. And we'd like to convert this into a quantum system. In fact, I'm going to do this initially for the free field only. We just spent some time worrying about the interacting field, but for the purpose of quantization, let's go back to the free field because it's simpler. And then later on, we'll include the matter degrees of freedom as well. But right now, let's just do free field in order to deal with the issues of quantization first. So for the free field, all I really need to worry about is the Hamiltonian for the field itself, which is right here, and then the definitions of the various field operators. The procedure I'll use is called Dirac or canonical quantization. And the basic idea is clear if I just write it out, is we take the Q lambda, the classical Q lambdas and P lambdas, and replace the Q lambda by an operator, which is multiplication by Q lambda, and replace the P lambda by an operator, which is minus IH bar ddq lambda. And this is has to be acting on wave functions psi that depend on the Q lambdas, of which there's an infinite number of them. There's one for each mode in the field. But if you like, you can think of the wave function for the electromagnetic field, free field now is all we're doing, as being a wave function that depends on this infinite number of Q lambdas that I introduced earlier. That's one point of view anyway. If we do this, then the operators that result, of course, satisfy the standard Heisenberg-Born commutation relations, that Q lambda commutator with P lambda prime is equal to IH bar times the Kronecker delta lambda lambda prime, and all other commutators, Q's with Q's or P's with P's are equal to 0. These are the commutation relations. This also, this then means that if I take the Hamiltonian for the classical field, which I can write this way as someone modes lambda omega over 2 times Q lambda squared plus P lambda. So this is one of the ways we had of writing it. It's the sum of the harmonic oscillators. This then can be transcribed into a quantum operator that acts on the state space of the system. And the formula is going to be the same because there's no ordering ambiguities here about Q's and P's. So the logical quantum operator is just the quantum harmonic oscillator, just adopted from the classical formula. If you wanted to, if you insist here, I could put hats on the Q's and the P's to indicate they're now operators. But I think for the most part, it won't be necessary for me to do that. In any case, the point is we can now get a sum of quantum harmonic oscillators. And we'll treat these quantum harmonic oscillators just like we always do with quantum harmonic oscillators. At least at first we'll do that. We'll introduce creation and annihilation operators. So we have A lambda is equal to Q lambda plus IP lambda divided by the square root of 2H bar. And we'll have A lambda dagger, the creation operator would be Q lambda minus IP lambda divided by the square root of 2H bar. And these are, of course, nothing but the quantizations of the normal variables we had at the classical level. So another way to quantize is to take the A's and A stars, the normal variables at the classical level, and just replace them by A's and A daggers. These have commutation relations that A lambda dagger prime is given by Kronecker delta lambda lambda prime, and other commutators are equal to 0. This follows from the commutation relations for the Q's and the P's up above, and the definitions of the A's and A daggers in terms of Q's and the P's. And that's in fact just like the harmonic oscillator stuff we did last semester. So there's really nothing new about that. And if we do that and follow the same procedure we used last semester, the Hamiltonian turns into the sum on lambda, that's to say for mechanical oscillators, if we use the same procedure, it's a sum on modes lambda of H bar omega lambda times A lambda dagger A lambda plus 1/2, where the 1/2 is the 0-point energy. And by the way, the A lambda dagger A lambda is the number operator, which we might call n sub lambda. It's a number operator for mode lambda. In any case, we get the nice Hamiltonian for the free field. Now, it's a sum of harmonic oscillators. Let's look at a single mode. Let's look at one mode. In that case, we can talk about the Hilbert space of the system. Let's call it E sub lambda. The Hilbert space for that mode is nothing but the usual Hilbert space for a harmonic oscillator. Single one-dimensional harmonic oscillator, that's all it is. I can write it in the form of the span of the basis states, which are the energy eigenstates. Let me call them n lambda here, where n lambda is the usual quantum number of the harmonic oscillator. It goes from 0, 1, 2, 3, and so on out to infinity. Let me get this off the screen a little bit. Let's call that E lambda. So that's just for a single mode. If I want the entire electromagnetic field, however, and I want the Ket space or the state space for the entire electromagnetic field, this must be a tensor product of these state spaces for the harmonic oscillators, I'll write it this way, as a product over the modes, and it's a tensor product of E sub lambda. And what that means is that a basis in the electromagnetic Ket space, you see this becomes quite a large space now because there's an infinite number of harmonic oscillators. A basis in the product space is just the product of the basis states. So this is a product over modes lambda, tensor product of the n sub lambdas, one for each. Well, the basis states is the collection of these things like this. And in other words, a basis vector in the product space is given by a sequence of harmonic oscillator quantum numbers n lambda, one for each mode. We can think of this as a string, an infinite string of quantum harmonic oscillator quantum numbers listed out like this. Because we put the field in a box, it made the modes, i.e. the degrees of freedom of the field, it made them discrete. So there's a countable infinity of them, and that means that you can order them in some order. You can number them 1, 2, 3, and so on. And so the n sub lambdas, which are the excitation quantum numbers of each of the modes, then strung together forms an infinite string of integers. And we can take this as specifying one of the basis states in the entire state space for the entire field. Let me denote that just by writing a ket in which we have, it's understood, an infinite string of integers like this. Now this basis, this forms a basis in our electromagnetic field state space. And for example, the Hamiltonian can be allowed to act on this basis, and in fact, it's an energy eigenbasis. The energy it brings out is going to be the sum over the modes of h bar omega lambda times n lambda plus a half. That's the usual energy of a one-dimensional harmonic oscillator, but it's summed over all the modes, bringing back the basis vector again. I mean, that's just a way of saying these are energy eigenstates. These basis states. These basis states, by the way, that I'm denoting here by these n, this is called the occupation number basis. The occupation number basis for the state space for the electromagnetic field. Again, I'll get this back on screen. That's what these things are. All right, so just by doing fairly trivial stuff with harmonic oscillators, we've got a set of basis states for the field. We know at the Hamiltonian, these are energy eigenstates, and a number of useful things like that. We got creation and annihilation operators. By the way, in this business of dealing with the quantum mechanics of the field, nobody ever uses these wave functions. I mentioned them a moment ago, but nobody ever uses them. I'm going to cross them out in red 3 times because nobody does it. What they do instead is they use Dirac's formalism of creation and annihilation operators on these occupation number basis states, and that's what we're going to be doing from here on out. So let me say some more about these occupation number basis states and also the creation and annihilation operators.
Professor?
Yes.
Could you turn the light up a little again? I think it got darker.
Yeah, let me try it again the same way. Maybe that will work.
That looks great. Thank you.
Good. I have a light on it, but the light is kind of dicey because if I turn it up too much, it just washes it out, and that doesn't help. Let me try it a little bit and see if that's better. All right. Yeah, thank you for telling me that. So for one thing, the creation and annihilation operators do their usual business, just like in 1D harmonic oscillators. If I have an occupation number basis state given by this infinite string of integers, and I apply an annihilation operator to it, it gives me the square root of n lambda. And then what it does is it lowers that particular quantum number to n lambda minus 1. In a formula like this, it's understood that all of the occupation numbers for all of the modes except the lambda mode are left alone. It's only the lambda mode gets lowered by a sub lambda. Likewise, the a lambda dagger raises things according to the usual formulas. So I get the square root of n lambda plus 1, and then I get an n lambda plus 1 here inside the ket. So this is a way of raising and lowering the occupation numbers. Also, if I have some set of occupation numbers like this, Oh, let's see, I'm not done yet. I need to introduce something else. Yeah, so before I get that, let me mention something else, which is the state in which all the occupation numbers are zero is of particular interest because it's the vacuum state of the free field. So if all the occupation numbers are zero, like this, we give a special terminology for this. We just write it as a ket with a single zero, and we give it a name too. It's called the vacuum state. So the vacuum state is the ground state of the field, the free field. The vacuum state has the property that if you apply any annihilation operator to it, you get zero. And likewise, the vacuum bra, if you apply a creation operator to it, you get zero because it's just Hermitian conjugates of each other. The vacuum, by the way, is a normalized state. Zero scalar product with zero is equal to one, just like because it's just harmonic oscillators. That's all. So it's just the ground states of all the harmonic oscillators. So it's a normalized state. Now, okay, so that's the vacuum, and given the vacuum, we can build up these states that have non-zero occupation numbers by applying creation operators to the vacuum. In fact, the formula is this: is that if I've got this string of occupation numbers which are non-zero, we can write this by taking the product over all the modes, the creation operator a lambda dagger, raise it to the n lambda power. We have to divide by the square root of n lambda factorial to make it normalized. And then that whole thing acts on the vacuum. So this gives us an explicit formula for an occupation number basis state in terms of the vacuum and the creation operators applied to it. All right, now let's take a look at the energy of the vacuum. We actually did the energy of the states a little while ago, I think. Didn't we? The energy eigenstates? No, I guess I didn't. Yes, I did. It's right here at the bottom of this page. If I, as I pointed out, the occupation number basis states are energy eigenstates, and if you apply the Hamiltonian, you just bring out the sum of the energies for all of the individual oscillators for the different modes. Let's apply this formula to the vacuum state. In that case, all the n lambdas are equal to zero, and we get a simpler formula. So what it is over here then is that H applied to the vacuum brings out an energy, which is a sum over modes lambda of just 1/2 h bar omega lambda. That's the vacuum, that's the 0-point energy of the modes multiplying onto the vacuum. So the vacuum is an eigenstate of the Hamiltonian with this energy. Now, unfortunately, this energy is equal to infinity. The reason is that it's finite for any given mode, but it's summed over all the modes, and the modes go out to infinity, and the omegas keep getting bigger and bigger. In fact, it diverges rather badly. It's a bad infinity. And so this means that the nominal ground state of the free electromagnetic field has an infinite energy. And this gives rise to interpretational difficulties. So you see, we've taken just 3 baby steps into quantum field theory, and we already have encountered an infinity. This is kind of the history of quantum field theory, is dealing with infinities. There's a number of ways of understanding what to do with this and how to proceed physically. Here's some arguments that need to be made. The first one is that in quantum mechanics, normally the location on the energy axis where we count E equals 0 is immaterial because only energy differences are physically important. So you can take any Hamiltonian and add or subtract a constant, and if you work through the quantum mechanics, there's no physical predictions that will be different. I mean, you might get some formulas that are a little different, but the final answers in terms of physics is always the same. So there's no relevance to where you count the E equals 0 point. This leads to a hand wavy argument that says, well, even though this constant is infinite, maybe we ought to be able just to throw it away and end up with by shifting the energy by an infinite amount, and then what we're doing is we end up with a vacuum which has 0 energy. See, the problem with this is not only the vacuum, it's not just that the vacuum has a non-zero energy, the energy is actually infinite. It'd be nice if the vacuum had 0 energy. That's what you'd expect physically. So if we just throw these terms away by an infinite shift in the origin of the Hamiltonian or the energy, that would do it. Now, If that doesn't sound like a very good argument, here's another argument. At the classical level, we had the Hamiltonian was given by the sum over modes lambda of h bar omega lambda times the normal variable a lambda star a lambda like this. Or it could have been written in terms of q's and p's, in which case we would have had the q lambda squared plus p lambda squared, similar sum. When we pass from classical mechanics to quantum mechanics, replacing classical observables by operators, there's always a question about the ordering of the operators, because operators in general don't commute, whereas classical observables do under multiplication. So classically, this a star a could be written as a lambda star. We could put it in the other order, and it would be the same thing classically. Now, if we work on the q and the p basis over a representation of the classical Hamiltonian, the q and the p don't commute with each other, but there's no products of q times p. So one might say that the quantization of that operator written in that form is straightforward and obvious, and it's just what we did a minute ago on writing down the quantum Hamiltonian, just basically put hats on the q's and the p's. On the other hand, we might have decided to quantize by writing the classical Hamiltonian in terms of normal variables, a's and a stars, and then quantizing by replacing them by a's and a daggers. And if we did that, we have a problem now, because the order does depend on the a's and a stars, and the a's and a daggers don't commute with each other. If we did this in one route, this would give us, in one ordering, this would give us an a lambda dagger a lambda. This would be the Hamiltonian without the 0-point energy. If we did it the other way around, you could write it in the other way, a lambda times a lambda dagger, which by the commutation relations you could reverse and you get a 1. The 1 would give you double the 0-point energy we just talked about. You could take the average of the two. That would give us the same 0-point energy we've been talking about. Which one is right? Well, on passing from classical mechanics to quantum mechanics, you can't expect to have a rigorous algorithm to do it. It's going to resolve these issues. The classical mechanics is only a guide to what the quantum Hamiltonian is going to be. Quantization is not a deductive process, because quantum mechanics has more physics in it than classical mechanics does. If those of you math types that want to talk to me about geometric quantization, talk to me in office hours and I'll tell you about it. But this is a different philosophy. This is physics and not math. And the fact is that classical mechanics doesn't do more than give you a guide to what the quantum system is. So you have to guess. And so which one is right? Well, the answer is we don't know which one is right. But the point that I'm making here is that the 0-point energy can be thought of as being tied up in the ordering ambiguities between that arise when we pass from the classical mechanics to the quantum mechanics. And so given the fact that we're just guessing anyway, we might as well make the guess that the correct ordering is the one that gets rid of the 0-point energy. All right, so that's another perhaps long-winded argument for getting rid of the 0-point energy, but at least it made some points that I think need to be made about the process of quantization. I think probably the most compelling argument for getting rid of the 0-point energy is actually a physical one. It is that physically the ground state is of the field is the minimum state of the field. We don't have an option. It is not physically possible to put the field in a lower energy state. And so the physics is that our energies, in other words, if we could go to a lower energy state, then somehow we might be able to extract this infinite 0-point energy and solve our energy crisis, right? Well, I mean, that's absurd. You can't do that. There is no lower energy you can go to. So the actual vacuum we have might as well be considered, from a physical standpoint, it really is the minimum energy we can come up with. So let's just count it as E equals 0. All right. In any case, that's what we're going to do for the rest of this course, is do that. We'll throw that away. And what that means is that henceforth, our quantum Hamiltonian then for the electromagnetic field can be written this way, as a sum on modes lambda of h bar omega lambda times a lambda dagger a lambda, but without the 1/2. This is going to be henceforth our Hamiltonian that we'll use for the electromagnetic field, which has gotten rid of the 0-point energy. Now, before I'm done with the 0-point energy, however, there's a few more comments to make, some interesting aspects of this. An obvious and good question is, we're just fooling around with theory here. Is there any experimental criterion that could be used to decide whether the 0-point energy is real or not. If you ask that question about a mechanical harmonic oscillator that has that 1/2 h bar omega down at the bottom, is that physically real? The answer is it certainly is. You can take in principle, one thing you could do is to take an harmonic oscillator in its ground state, and you could take the spring constant and change it. Suppose you can change it as a function of time, slowly change it to make it go to 0. That would make the frequency go to 0 too. And it would make the Gaussian wave packet for the ground state gradually expand and spread out. And as it does so, it would do work. And the work that you get out of it ultimately turns into the ground state energy, 1/2 h bar omega. I mean, this is kind of a abstract a thing to do, but a statement is an abstract argument I'm making. But the point is that it is, in principle, it's physically possible to access that 1/2 h bar omega. There's no question that it's really there. So what about the electromagnetic field? Well, in the electromagnetic field, we can't change the modes, the frequencies and the modes of the field. There's no spring constants we can modify. So we don't have that option. However, there is something you can do with the electromagnetic field. You can introduce conductors, which change the boundary conditions on the electric and magnetic fields, and therefore they change the mode structure of the fields. For example, let's suppose we consider parallel plate capacitors. A capacitor, let's say there's a length L, distance L between the plates. Let's put in these plates and let's idealize them as having infinite conductivity at all frequencies. Then the modes of the electromagnetic field inside the plates anyway look like, a particle in a box. You've got a mode looks like that, and another one looks like that, and so on. And the point is that the presence of the conductors has changed the modes of the field so that they aren't the same as what they were in open infinite space for the free field. Now you can go through the same procedure we went through, expanding the arbitrary field in terms of the normal modes and introducing mode amplitudes, and then getting harmonic oscillators for the classical evolution, and then quantizing them, just what we did for the free field. And if you do that, you'll find an infinite number of modes. And once again, you'll find that there's an infinite 0-point energy in the quantized oscillators. So it didn't seem to help putting in the conductors. Nevertheless, as it turns out, interestingly enough, it turns out that it's possible to make sense of the difference between the infinite 0-point energy that exists when there's no conductors. That's what we just done a minute ago. And the case in which there is conductors, and moreover, that difference can be, it turns out to be finite. I skipped the details, but I'll quote you the formula. The formula is this, is that you get an energy, which is really the energy difference between these two infinite energies. This really has an infinity minus infinity. And you have ways of arguing that the ultraviolet tails cancel, leading to a finite sum. And this is an energy, it's actually not an, when I say finite energy, that's actually not correct. Because in the case of parallel capacitors, it's a finite energy per unit area. The total energy is infinite because the capacitors have an infinite area in this ideal model. It's a finite energy per unit area. So let me write it as E over A. That's the finite quantity. And it turns out it's negative, and it's given by pi squared h bar c divided by 720 L cubed, where L is the distance between the plates. Interestingly enough, it depends on the distance between the plates. The actual calculation of this result is somewhat lengthy because of the vector nature of the electromagnetic field and the mode structure and a lot of things like that. And it's a three-dimensional problem and so on. But if you do the analogous problem for a one-dimensional scalar quantum field theory, the calculation of the difference between these two energies is not that hard to do. You could do it as a homework problem. I won't inflict it on you, but one can do it. It's not that hard to get the answer. So I want to just say, first of all, this answer is not that difficult to get. It's not that difficult. Anyway, the interesting thing about it is that it depends on the distance. And so what that means is that if you were to vary the distance between the capacitor plates, you need to do work in order to make up for the difference in the 0-point energies between the different configurations. And so that in turn implies that doing work means that there's a force that's required to move the plates. And this in turn means that there's a force between the plates. Well, it's actually a force per unit area, to be more precise. The force per unit area is the same thing as a pressure. And that's given by minus the derivative with respect to the length of the energy per unit area. And just taking the derivative, this turns into minus pi squared h bar c divided by 240 L to the fourth power. And so we end up with a prediction that parallel plate capacitor, parallel plates of a capacitor experience a force per unit area between them caused by the vacuum energy of the electromagnetic field. And what's interesting about it, of course, is that you can check it experimentally. This is called the Casimir effect. It was pointed out by Casimir in the late 1940s. And it was confirmed experimentally by the 1960s. It turns out that the experiments work, the force is really there, and with an experimental error, it agrees with the theory. So one would say, yeah, it looks like there is some reality to the 0-point energy. So it's a very interesting question, for the whole business. In any case, going forward, we're going to ignore the 0-point energy and drop the term from the Hamiltonian, which is appropriate for the free field, and we're going to do that henceforth. Okay, are there any questions about what we've done so far? Setting up the basics of quantization, the occupation number basis, the Hamiltonian, the 0-point energy, the rationale for dropping it, and so on. Any questions about all that before we go on?
I just wanted to quickly ask if there was any sort of reasonable way of understanding how to change basis from this occupation basis to the basis where elements are wave functions of q lambdas and p lambdas.
If you think about it, you'll see how to do it, because each of these n lambdas is just a Hermite polynomial. It's a Hermite wave function. So the wave function equivalent of that is just a product of an infinite number of Hermite things. And if you think about it in those terms, you'll see why nobody does that. Nope, nobody wants to talk about, go look at the formulas for Hermite polynomials. You'll get it right away. Okay, but if you want to do it, you can do it.
I have a question.
Sure.
We were writing these kets as discrete lists because we did this box normalization, but how are we going to make sense of, like, when we try and take the infinite limit?
I'll get to that.
How are we going to write that?
I'll get to that. Maybe not tonight, but I'll get to that. I'll show you how you do it. Yeah. All right. Now, once we've done this tricks with the 0-point energy, then the Hamiltonian, acting on an occupation number eigenbasis, brings out an energy which is the sum on modes lambda of h bar omega lambda times n lambda, which is what we call the occupation number. Hence, that's why this basis is the occupation number basis. And what we see is the total energy of this energy eigenstate is the sum over modes. And for each mode, we have an integer multiple of h bar omega. Now, this should remind you of the original photon hypothesis of Planck and Einstein. Actually, Planck never hypothesized photons. Planck hypothesized that energy was transferred between matter and radiation in unit multiples of integer multiples of h bar omega. Einstein insisted that those multiples applied to the field itself, to the energy in the field, and moreover, he connected them with particles. He didn't call them photons. That name wasn't coined until about 20 years later, 1926, I believe. And the person responsible for that was C.N. Lewis, who was chairman of the Berkeley chemistry department at that time, for whom the building is now named. Those of you who are confined by COVID might never have seen it, but maybe someday you'll be able to get out and see it. Anyway, he's the one that coined the name, but by whatever name, Einstein was very clear that he was talking about particles of light already in 1905. And he not only ascribed them an energy, but also momentum, which I'll get to in a minute. People thought he was insane because, you see, there's a history of this. Newton had to believe that light consisted of particles. Not exactly a stupid idea, considering the way they travel in straight lines and so on. And he wrote a book about it too. However, in the early 1802, experiments by Thomas Young showed that light exhibited wave phenomena, interference and diffraction. And so it became, so the corpuscular theory of light was rejected as being wrong, and light was understood as a wave. And then of course, in the rest of the 19th century, Maxwell's electromagnetic theory of light was the greatest triumph of the entire, theoretically anyway, of the entire century. So by the time of Einstein, it was a deep article of faith that light was a wave and not a particle. So people thought he was utterly crazy for saying this. But in any case, this led to the photon hypothesis. By the way, nobody took the photon hypothesis seriously until the results of the Compton experiments came in around 1923. But of course, in the end, Einstein proved to be correct. And what you can see coming out here is that the energy in each mode is an integer multiple of h bar omega. This is just what Einstein said. And so this is leading us to the conclusion that these occupation number eigenstates are states of the free electromagnetic field in which mode lambda has n sub lambda photons in it. And that this is therefore is the occupation number of that mode in terms of the number of photons, hence the name for the basis, the occupation number eigenbasis. All right, now, so that's the beginning of the connection with the theory of photons, and we'll continue to fill out the rest of this theory. Einstein said not only does a photon have an energy h bar omega, but he said it also has a momentum p, which is equal to h bar k, where k is the wave number of the corresponding mode. Let's turn our attention now to momentum in order to understand the momentum of the photon. What we need is a momentum operator for the quantized field. We have the Hamiltonian right here, that's the energy. How did we get the Hamiltonian? Let's remind ourselves. Well, we had the classical Hamiltonian, and then we quantized it by using Dirac or canonical quantization, modulo 0 point terms that we threw away. Can we do something similar for the momentum? Well, let's do that. Let's go back to the classical momentum of the classical electromagnetic field. This can be worked out via Noether's theorem, or again by integrating components of the stress energy tensor. It has two, if we talk about the interacting field, it has two terms. One is the sum over particles alpha, mass m alpha times velocity v alpha. And then there's a contribution from the field, which is 1 over 4 pi c times the integral over space d cubed x of E cross B. Now, right now I'm talking only about the free field, so I'll throw out the matter part, but you'll notice that the matter part is just the kinetic momentum of the mass, the matter particles, mv. This is again a non-relativistic treatment. As far as the field part, E cross B is of course proportional to the Poynting vector, which is normally thought of as the energy flux, but it's also proportional to the momentum density. And that's what we're doing here is we're integrating the momentum density over all space. The 4 pi c is the right prefactor to get the total momentum of the electromagnetic field. For the free field, the E part is just the transverse part. So it's purely transverse. So I can put a transverse subscript in that if I want, when I'm talking about just the free field. Now then, I'd like to express this in terms of more interesting operators like Q lambda, P lambda, or maybe A lambda and A lambda dagger. The way to do that is get the Fourier series for the electric and magnetic fields. And I flashed them by you before, but let me bring them back again. Here they are. No, let's see, where are they here? I wrote them in terms of A's and A daggers. No, I'm sorry. Let me get it right here. Yeah, here it is. This is the page I want. It's down here at the bottom. This is where I wrote the Fourier series for the three fields in terms of A lambdas and A lambda daggers. So the electric field, you see, it's got a annihilation and a creation operator. So does the magnetic field. So does the vector potential. By the way, let's look at the structure of these fields. The X here, as I keep saying, is not an observable. It's just the location at which you make the observation, for example, of the electric field. You go and you measure electric field at position X. The E is the observable. Therefore, the E is the operator that needs to act on the state space of the system, and that's just a mess over there. So the E is the operator. And it does so because the A's and A daggers, oh, excuse me. This was the classical formula here. That's why there's A stars. These are the classical fields written in terms of normal variables. But to quantize these, to convert these into the corresponding quantum operators, we replace the A's and A stars by A's and A daggers. So I'll do that with my red pen, and I'll just take that star and make that a dagger, that star, make that a dagger, that star, and make that a dagger. And otherwise, the formulas are the same. All right, so with those changes then, what we now have is 3 examples of quantum fields. A quantum field is an operator valued field over in 3-dimensional space. It's an operator which is a function of position x. And it's an operator that acts on the state space of the electromagnetic field precisely because of these A's and A daggers that appear on the right-hand side. The rest of this is just C number stuff insofar as the action on the state space for the field is concerned. So the momentum, the classical momentum involved the integral of E cross B. Here they are. If I went back to A stars instead of A daggers, I could multiply these 2 Fourier series together and integrate out and get a useful expression for the classical momentum of the field. But what I wanted is a quantum expression for the field. So what I'm going to do is to take that classical expression, replace the A's and A stars by A's and A daggers to quantize them. And then I've got the same formula, which is here. It's this integral, except now the E and the B are quantum fields. If I write out the structure of this, it's going to be 1 over 4 pi c. It's going to be the integral d cubed x. And then the E and the B is going to be, there'll be 2 series multiplied together. So it's a double sum on modes like this. And the general structure of it is that for the E series, for the E Fourier series, there's A lambdas and A lambda daggers, and that gets crossed with the magnetic series, and that's also A lambdas and A lambda daggers, like this, except I'll put primes on the lambdas here because it's different modes. Anyway, this is the structure of the integral, like this. Now, this gives 4 terms, and you can multiply them out and do the integrals. And I'm not going to do it because I did a similar calculation for the energy earlier in a previous lecture, and it's straightforward, but somewhat tedious to write it all out. So I'll leave it as an exercise for you to go through. I think actually most of it is displayed in the notes if you want to look at it. But the net conclusion is that the thing that comes out, the main thing that comes out, is that you end up with an expression for the momentum, which kind of has a 0-point momentum, just like an infinite 0-point momentum, just like we had an infinite 0-point energy in the case of the electric field. In the case of the energy, in calculating the energy, we ended up with an infinite 0-point energy, and doing the naive thing here for the momentum was going to again give us infinite 0-point terms. So what's going on? Well, one way to see this is to look at what would happen if I took the expectation value of the momentum operator with respect to the vacuum. We'd like this to be 0. It's physically, it ought to be. And what you can see here is if you multiply these 2 series together, one of the terms you're going to get is an A times an A dagger like this. You're going to get terms that go like this: a vacuum, an A lambda, and an A lambda dagger, and then the vacuum like this. Now that term is significant because that term is non-zero. It has a creation operator next to the vacuum ket and an annihilation operator next to the vacuum bra. The other terms, the one that have the annihilation operator next to the vacuum ket, that would go out. And the creation operator next to the vacuum bra, that goes out. This is the only one that doesn't go out because of annihilating a vacuum. So this is the problematic term that gives us a non-zero answer, which in fact turns out to be infinite. This would work out all right if the dagger terms were to the left of the undaggered terms, but they aren't in just the multiplication of the Fourier series. So this leads us to some notation. The notation.
I have a question.
Yes.
How does that equation with the A lambda and A lambda dagger, how does that turn into a vector?
It's because I'm suppressing a lot of details here, but these are Fourier series for the electric and magnetic fields, and they got polarization vectors, and magnetic series has got a K cross polarization vector. So there's vector stuff in here. I just didn't write it all out.
Okay. So even like the 0-point momentum ends up having.
Yeah, it's going to have a vector in it too. Yeah.
Okay.
So it's going to end up pointing in some direction, right? All right. Anyway, Now, so here's what we do. Let's let Q be a polynomial of A's and A daggers, like this. Then we'll define what we call the normal ordered polynomial, and the notation is surrounded by colons, normal ordered. And the normal ordered polynomial is obtained by taking all the A daggers that are in it and moving them to the left, and taking all the A's and moving them to the right. And if you think about doing this by means of commutators, of swapping the positions, we drop the commutators in doing it. In other words, we ignore the commutators. And that defines what this thing is. That's the normal ordered polynomial. Another point of view of this is to say, suppose the polynomial is not in A's and A daggers, but A's and A stars. Suppose it's a classical polynomial. Now we move all the A stars to the left and all the A lambda and all the A lambda, the unstarred A's to the right, which we can do for free in the classical theory because they commute. And then we quantize. So we delay quantizing until after the ordering has been done. In any case, that gives rise to the normal ordering. So in this momentum expression, if I had normal ordered things, if I put a colon there and a colon there, then this bad term would have been normal ordered. It would have been moved, the dagger would have been moved to the left. And then all four of the terms that we got by multiplying this out would have given us a 0 vacuum expectation value. And so with that notation, and this gives us an idea about how to define the momentum operator for the field. And by the way, we can go back to the Hamiltonian too, and we can write it in a different way. We can write the Hamiltonian is 1/8 pi, the integral over space d cubed x. And now what we have is the normal ordered e squared plus b squared. And if we do this, this turns into sum on lambda of h bar omega lambda, a lambda dagger, a lambda. Now here it's understood these are the quantum fields, the electric and magnetic fields. The normal ordering gets rid of the 0 point. Likewise, we'll define the momentum operator as 1/4 pi c integral d cubed x of the normal ordered version of E cross B. And if you go through the calculation, which is mostly outlined in the notes, what you get is sum on lambda of h bar k times a lambda dagger a lambda. The a lambda dagger a lambda, of course, is the number operator. But the point is there's no 0 point in here. And so it's a formula rather similar for the momentum as it is for the energy, except it's h bar k instead of h bar omega. That means the field momentum operator applied to an occupation number basis state. But what we find is that this is not only an eigenstate of energy, but it's also an eigenstate of momentum. And the momentum is the sum on lambda of h bar k times n sub lambda, summed over the modes. And so this gives us a pretty picture of both energy and momentum then for these occupation number eigenstates. All right. All right, then. Are there any questions about that? That's the energy and momentum of the field. The angular momentum of the field can be treated similarly, but it's a good deal more complicated. And so I'm going to postpone it until later. And I'm only going to give an incomplete treatment of it. But this is how we deal with the energy and the linear momentum of the field. It also confirms Einstein. You see, the photon has momentum h bar k. All right. By the way, if the energy is h bar omega and the momentum is h bar k, then because of the dispersion relation for light waves, this means that E is equal to Cp. And this is the energy momentum relationship for a particle which travels naturally at the speed of light, a massless particle traveling at the speed of light. Now, of course, Einstein knew about special relativity, so he was very aware of this. But these particles of light that he was coming up with, he understood that they were massless particles that necessarily have to travel at the speed of light. Okay, so we're out of time. Are there any questions about what we covered tonight?
I just wanted to quickly ask why. So I get how we can subtract, like with with energy, we can always define what we mean by a zero, but with momentum, that's not true, right? Like in a reference frame, either the particle is moving or not, right? Momentum doesn't have that arbitrariness in definition. So what is
Well, if you
our
went into a reference frame,
argument there to be able to?
yeah. So I suggest you try going through the calculation of the momentum operator when you don't assume normal ordering, and you'll see the trouble you get into. Actually, it's been a long time since I did it, so I can't tell you what the details of it are, but it's clear when you do it, this isn't right. But it's the same kind of being wrong as appears in the calculation of the energy that is the Hamiltonian, ending up with that 0 point energy. Once again, it can be regarded as an issue that's tangled up with the ordering ambiguities in the classical observables when we go over to from the classical to the quantum system. Any other questions? All right, if there's no other questions, then I thank you for your attention, and we will continue this on Thursday.